So, good evening, everyone, and welcome to this special lecture this evening as part of this Fermor 2012 meeting. So, 3 years ago, the man on my left there, Paul Hoffman, known to some of you, was awarded the Wollaston Medal, which is the highest medal of the Geological Society of London. So, a great honour, and one where we expect the medalists to come to London, especially to receive the medal. This guy didn't turn up. Now, the usual excuse is, I'm in Namibia. No, it's always, I'm in Namibia, I'm too busy. But no, there was a real reason, and he wasn't able to run marathons for a while, but his health recovered. He's certainly been running marathons since. He tells me that now it takes him as long to run a kilometre as it used to take him to run a mile. So when it comes to running, because of the elastic forces involved, he's a little bit slower. But there's lots of other things where he's just as damn good as ever. And we're going to hear one of them now, which is his ability to deliver a fine lecture. So over to Paul to talk about climate science and geology, a tale of three histories.
Thank you so much, Ian. I have to say I'm thrilled to give this lecture, not least because 40 years ago, Janet Watson and her husband, John Sutton, were extremely encouraging to me at an early stage in my career. How about this? Okay. Now, as some of you know, I've fallen into the habit in the last few years of reading old papers. The older, the better. And so I hope you will enjoy this evening when I describe to you some of the things I've found concerning interactions between geologists and physicists during the early development of both geology and climate science. And I think that it must be said at the very outset that climate scientists developed a comprehensive understanding of the climate system without reference to geology. However, when it comes to climate change, global climate change, geology has played a very important role. And I'm glad to be able to point this out because, of course, one of the reasons for the outstanding turnout at this meeting has been this great increase in interest in Neoproterozoic Earth history and cryogenian Earth history in particular, which is almost entirely due to the interposition of climate modeling into the world of geology. Now, I want to preface the talk with this one slide, and incidentally, this talk is only about 35 slides, so I hope to finish in the hour and leave time for questions. But I want to preface this talk. You see, there were some people who know me well enough that they were concerned that afterwards we would retire to breakfast. So this is a glacier, or a pair of glaciers that are retreating, even in 1990, and they leave behind a tongue of sediment which can be recognized as glacial in origin by any sedimentologist with a decent amount of training. And that means we can tell with a good deal of confidence where ice sheets existed that have now vanished. And this is scale independent, of course. It doesn't matter whether it's a small glacier like this or a large glacier like the one that covered most of Northern Europe and North America not so very long ago. So that's the preface for the talk. And I'd like to begin by telling you about a physicist who got the geology completely right decades before any geologist, but only because he had the physics completely wrong. So John Wesley was professor of mathematics and later natural philosophy at the University of Edinburgh at the beginning of the 19th century. He was a protege of John Playfair, another mathematician well known to geologists as the author of the illustrations of the Huttonian theory. And Wesley was the mentor of the great Scottish glaciologist James David Forbes. Now, Wesley was also a nearly exact contemporary of Fourier, the French mathematician and physicist. And like Fourier, Wesley's main interest in science was in the nature and propagation of heat. And Wesley recognized that the Earth is being heated by solar radiation. And he calculated that the entire Earth should warm by 1 degree every 2,400 years, approximately, as a result of what he called the accession of the solar rays. And what's interesting about this idea is that he sought geological evidence to support his idea of global warming. And so in 1796, he and the pioneer Scottish photographer Thomas Wedgwood went on a coach trip up the Rhone River to the head of the Rhone and up and over the Grimsel Pass and down the River R with a little side trip into Grindelwald to see more glaciers in addition to the ones he saw at Grimsel Pass. And Wesley writes in a long appendix of that book, his most famous book, published in 1804, that any tourist can see that these curved ridges of loose angular stones that the local Swiss people call moraine, which are increasingly vegetated with distance from the active glaciers, represent the positions of the terminations of those glaciers at an older and colder period. And he recognized that these moraines went down 750 kilometers below the present snow line, the line of permanent congelation, as he called it. Now, of course, it's very easy to see these moraines today. This is the many switchbacks on the road up to Grimsel Pass. This is the village of Fletch. And there's a series of moraines here that represent the retreat of the Rhone Glacier. But, of course, at the time that Wedgwood and Wesley were there, those moraines were covered by ice. So this is the village of Fletch in 1870, and the Rhone Glacier is almost in the village. So, of course, Wesley wasn't talking about the Little Ice Age. He wasn't looking at it from this vantage point. He was looking at it from this vantage point. This is really a horizontal line with the advances and retreats and advances and retreats of two of the major alpine glaciers. And this is the date of his visit. And so, of course, Wesley was talking and describing a much more profound ice age, a time when the entire Swiss Alps were covered by ice. And so he had, in fact, discovered the last glacial maximum. And, of course, he rejoiced because the evident warming that has taken place since that time fitted beautifully with his idea of global warming, which, however, could not have very much pleased his senior contemporary in Edinburgh, John Hutton. Here is North America, of course, from T.C. Chamberlain's map and James Geeky's book. These ice sheets have had a profound influence, not only on the geology, but even on the politics and sociology of Canada and the United States. All the soil from central Canada is down here. Canada is a wonderful place to be a prospector. Canadians are a lot like prospectors, always hoping for the best and seldom finding it. Americans are more like farmers, fearing for the worst and finding it everywhere. Now, the problem with Wesley's theory, of course, is that within a few million years, the entire Earth would be molten. And so there's obviously something missing. And what was missing was infrared radiation, which wasn't discovered until 1800 by the German-English physician and astronomer William Herschel, assisted by his sister Carolyn, a very respectable astronomer herself. In 1800, for reasons that aren't exactly clear, Herschel decided to measure the caloric energy of light across the visible spectrum of light, and seeing that the energy content increased as the wavelength decreased, he kept on measuring into the infrared and discovered a peak of energy that lies outside the visible spectrum of light, and inadvertently discovered infrared radiation, which the Earth itself emits. Now, a couple of decades later, enter Fourier, Leslie's contemporary. And Fourier points out that something very obvious and also very profound. And basically is that the hot objects give off more heat than cold objects. And if the object under consideration is the Earth, if the Earth started off hotter and gave off more heat than it received from the sun, it would cool down until the heat it gives off equaled the heat it receives. And conversely, if it started off cold, it would receive more energy from the sun than it was giving off and would warm up. And it would continue to warm until that radiative balance was achieved. And this was a very important concept which leads to a proper understanding of a number of phenomena, but which also had a consequence, and that is that the global surface temperature is slave to the sun. And of course, all physicists in the 19th century assumed that the sun was getting colder over time. It was a large, hot object, was losing energy through radiation, and so therefore it must be cooling. And this, of course, is the reason why Kelvin preferred the lower of his estimates of the age of the solar system and of the Earth, 20 million years, because that was more consistent with estimates of the age of the sun. He was, of course, motivated to destroy Darwin because, being a good Presbyterian, he was appalled by the amorality of natural selection. He knew about convection. You see, the problem with his model was not that he ignored radioactivity. Radioactivity hardly does anything. It's that he ignored convection. Convection mines heat from the deep interior and delivers it upwards to the base of the lithosphere, maintaining a steep conductive gradient in the lithosphere that Kelvin assumed goes all the way to the center of the Earth. So that meant that if the sun was cooling, then the global surface temperature must be cooling slowly as well. And of course, there was a lot of geological evidence that supported that. In the Eocene, there were palm fronds all over the place throughout France, where hardly any palms grow today except on the south coast. It was also historical evidence. It was well known that the medieval period was a lot warmer than the Little Ice Age, which Europe was still in. So there was both geological and historical evidence to support the idea that global climate must be getting colder over time, consistent with a dimming sun. Of course, this business about the radiative balance proved to be extremely important and highly quantitative, and it is because of this relationship here that was demonstrated experimentally by these two from the University of Vienna, the elder Stefan, who did it experimentally, and then, of course, the brilliant Boltzmann derived it from first principles in a way that allowed this term here to be predicted and experimentally confirmed. And this is actually one of Boltzmann's, I suppose, more minor achievements. He also developed statistical mechanics, which Planck so reluctantly applied to explain black body radiation and creating the non-hysterical period of the initial development of quantum physics. Meanwhile, geologists were at the front door of a huge controversy of their own concerning the quaternary drift. And these are some of the features that geologists were struggling to understand: tills, striated pavements, U-shaped valleys, erratic boulders of compositions that are completely unlike the bedrock on which they sit, and which in many cases can be traced for tens, even hundreds of kilometers upstream. Now, this was a great controversy, but one thing that needs to be made clear, and that is that the idea that it was a colder period during the drift period than it is today was not controversial among geologists. The geological controversy was whether these deposits and landforms are associated with floating ice or grounded ice. It seems a rather minor point, actually, if you look at geology from the outside. But that's really what the glacial controversy was about. It was non-controversial, for reasons I'll explain momentarily, that the drift period was colder. But you can see it represents a problem for physics. So, of course, the glacial controversy is most closely associated with Louis Agassiz, who was awarded the Wollaston Medal at the age of 26 for his work on fossil fish. He's still the youngest ever awardee of the Wollaston Medal. So, as a young professor at Neuchâtel, when he gave his famous address to the Swiss Academy of Natural History in 1987 as the professor at the host institution, he shocked everybody by not talking about fish, but by a theory that he got from the nets via Charpentier of the idea of a great glaciation that covered the entire Alps. And in Agassiz's view, hoping to account for the last great mass extinction, Agassiz was Cuvier's last postdoc, and unlike Cuvier, who was not religious, Agassiz was. Agassiz was looking for an explanation of that last great mass extinction that preceded the appearance of the modern flora and fauna, including man. And he thought he saw it in this glacial theory, was developed most importantly by Venetz, the Swiss road engineer of Canton Valais. And Agassiz made it controversial by force of personality and ambition and hard work, all three of which he had in great abundance. Here's my depiction of the glacial controversy. It's simply a histogram of the papers and books that I've read. It's not a huge number. It's only about 350 or so, but it beautifully describes the history of the controversy. And like many controversies in science, it has four stages: a stage of neglect, a stage of hysteria, rejection, and acceptance. Neglect is the period when many people had basically the right idea. Here's Wesley. But they only wrote one paper. And nobody convinced a science of a radical idea with one paper, certainly not in earth science. And so nobody paid any attention. Okay? But Agassiz, in Britain, with the help of the great William Buckland, as flexible and as open-minded as ever late in his career, Agassiz made it controversial, this period of hysteria, as I call it, and hysteria because of the reaction to Agassiz's ideas. It's very interesting. I don't have time to go into. Anyone who's interested, we could talk about it later. I have ideas as to why there was a sudden drop-off. I'll explain one of those ideas momentarily. Then, of course, there's the period of rejection. In this case, it's 25 years. Many other controversies is much longer. Natural selection, 80 years, okay, between 1859 and the neo-Darwinian revolution of 1942, plus or minus 4 or 5. Plate tectonics, 60 years. This is only 25 years. I think it's about the minimum. There has to always be a period of rejection. And that is best phrased, paraphrased by Max Planck himself. Science advances one funeral at a time. Okay? So the Scottish revival, Ramsay, Thomas Jamison, the Geeky brothers, James Kroll also, all these people were either children at this time, or in the case of Ramsay, he was an adult, a young adult, but not in geology yet. They worked hard during this period in systematic mapping and research on the assumption that Agassiz was wrong, and when they put all their results together, they said, whoop, he was dead right after all. And from that point on, almost everybody fell in line. Here we go. Now, here's a person who's a little bit overlooked. This is the legendary yachtsman from the Clyde River, James Smith, not to be confused with William Smith. He was also a significant biblical scholar and other writer. And in this paper, which was presented in extended abstract in the proceedings and then 3 years later in the transactions in more expanded form, note the title, On Indications of Changes in the Relative Level of the Sea and Land in the West of Scotland. And when you go to papers on the drift, there are way more papers that are written about these changes in the relative level of land and sea than in the deposits. And the relative levels of the land and sea plays a critical role in what happens. So James Smith described the drift. And of course, the drift was problematic because it was the next to the alluvium, which has human remains and agrees perfectly with the modern landscape. This was the next youngest strata, the diluvium, it was sometimes called, or drift. And if you couldn't understand these almost recent deposits, what chance would you have of working out the history from older strata? And of course, the early 19th century geologists were consumingly interested, to huge approval from other scientists and politicians and the general public, with these eye-opening discoveries when they started to systematically look at the fossil and the geological record period by period and zone by zone, working backwards progressively from the present. But if you can't understand the next to recent, you have a problem of credibility, if nothing else. So what James Smith noticed was that there was often a layer of massive till. He's the first person to use in the geological literature this old lowland Scottish term for a, in James Smith's words, stiff, because it had ice sitting on it, non-stratified clay confusedly mixed with boulders, with rare stag's horns, this is Megaceros, so-called Irish elk, elephant tusks, these are mostly mammoth, mammutus. Incidentally, mammoth is a Siberian Eskimo word for a large animal that lives underground. And bones, and local marine fauna, okay? And then it's often overlain by laminated clay, as opposed to this massive stuff, with marine fossils of modern Arctic aspect. So this guy is an amateur conchologist. So he sails this boat and he drags the seafloor for mollusks, which he identifies. And so this guy has sailed all around Scotland. He's sailed all around Iceland. He's even been up a little bit on the forbidding southeast coast of Greenland. He's been all around Svalbard, and he knows his mollusks. And what he notices is that there's been a big change. Now, both of these deposits have marine fauna, and they occur well above sea level. And so this is the situation. Often sitting on terrestrial beds, you have the massive till overlain by the stratified till, marine fossils in both, and they're both standing above sea level. So obviously, during the drift period, sea level was higher than it is today and has been going down ever since. And so you can see that this idea that the ice was coming in, floating ice from the Arctic associated with this big rise of sea level, of what origin, is not a completely crazy idea. Although it's rather non-uniformitarian for an idea that was championed by Charles Lyell, who almost to the end did not accept the glacial theory. He accepts it finally in the last edition of the Elements of Geology. Motivated, incidentally, by Hans Rink's paper called Giant Icebergs in the West of Greenland. And the Rink, this 1852, recognized that the whole interior of Greenland is a vast accumulation zone of ice that is exiting out of not more than 9 narrow outlets, of which Jakobshavn, Ystrom, he personally mapped and understood well. This is the Scottish glacial revival. These are the guys who finally said, well, Agassiz was right, and documented it beautifully. And in many ways, the key person here is Thomas Jamison, a soil scientist from Aberdeen. And it was Thomas Jamison who first resolved this problem. But he resolved it after everyone had accepted the glacial theory after all, despite the fact that this evidence of sea level rise runs exactly counter to the predictions of the glacial theory. If you accept Agassiz's theory that Europe, North America, and he also thought much of Northern Asia were covered by ice, sea level should have been 250 meters lower during the drift period than it is today. But the geologists all observed, that is the British and the Scandinavian geologists all observed the evidence that sea level was higher. So a major prediction of the glacial theory ran completely against geological evidence that all geologists knew and accepted. And there's a great amount of literature discussing whether these fossils could possibly be reworked. And they finally decide, when you see articulated whale bones and articulated bivalves, they have to have been living there. So the glacial theory had a real problem with this geological evidence, and Thomas Jamison was key because he was the first person to point out that not only could the ice sink under the load of this enormous mass of ice, but moreover, like a heavily laden train that crosses a wet embankment, the rails go down, but the embankment rises. And so just beyond the edge of the ice, the land tends to bulge up. And that bulge can increase or decrease in concert with the advances and the shrinkages of the ice sheet. Moreover, he pointed out something else, and that is that the mass of the ice itself, by adding to the volume of the continent, draws the water towards it. And so the sea level tends to rise locally in the vicinity of the ice sheet. And that water will go up and down in concert with the expansion and shrinking of the ice sheet. Now, you know, if we wake up tomorrow morning and the Greenland ice sheet is gone, although global mean sea level may have risen, sea level around Greenland, around the edge of Greenland, will drop dramatically by tens of meters because of the loss of that gravitational attraction. I mean, people write papers in Nature, based on this concept that Thomas Jamison wrote up in 1882 in a qualitative way. Okay, so James Smith noticed that during the drift period, the mollusks are very, very similar, 85% present species, still extant. So that shows the deposits are very young. You know, this is how they measured, they dated the Cenozoic, was basically by the percentage of species in a fossil assemblage that are still extant. And of course, that percentage goes down as you go into the past. So 85% modern species, so very recent, but during the drift period, the assemblage that are down here are like those that are presently in Svalbard. And as evidence mounted for successive advances and retreats of the ice, it became clear from work on land in fossil sections that the fossils had done this also. Now, this means that these assemblages are migrating on the order of 1,000 kilometers north and south at the high latitudes. And so that means there is significant climate change that is reversible, that is going back and forth. And of course, the problem is that there was no physical explanation at that time, either for global warming or for bidirectional climate change. And so that represented a huge challenge to climate theory. Okay, so John Tyndall was born in very poor circumstance in south central Ireland, and he got a job as a surveyor's assistant in England and rose rapidly in the British public service. And he was something like the Carl Sagan of his time. He was not only a great scientist, but he was a great orator and writer and champion of modern science and technology, for that time. And he was a physicist. He was also a glaciologist and a mountaineer. In a series of experiments in 1861, he decided to test an idea that had first been suggested by Fourier, but Fourier didn't really believe it had any influence on climate. And that was the possibility that there were components in the atmosphere that might absorb infrared radiation but be transparent to sunlight. And so he did experiments using pure gases, nitrogen, oxygen, water vapor, carbon dioxide, and ethylene. And he studied their absorption both in sunlight and in infrared radiation. And what he found, of course, was that water vapor and carbon dioxide were strong absorbers in the infrared. And as he put it, he's a marvelous writer, he said, water vapor represents a blanket more essential to the vegetable life of England than clothing is to man. You'd kill to be able to write like this. And he understood perfectly well, however, that water vapor content of the atmosphere is itself a function of temperature, almost entirely. And so therefore, it cannot be a prime driver. It's only an amplifier of any imposed change. And so something else must be present to explain what he called all the mutations of climate that the researchers of geology have revealed. It's one of the things I love about Tyndall. He's very open about the motivation for these experiments. And so what he finds, of course, is that carbon dioxide is also a small absorber. And although he didn't really understand how carbon dioxide could change, because unfortunately the guy who could have explained it to him, Joseph Abelman, had died at a relatively young age, at least 10 years earlier. And of course, Abelman's writings were 20 years earlier, and there's no evidence that I can find that Tyndall was aware of them at all. However, he did isolate CO2 as a potential driver of climate change. Now, that's 1861, 1862. There's a pair of papers. And it took 100 years before carbon dioxide greenhouse became well accepted in the climate physics and general community. And there were a lot of objections to it. One is that at the surface, the absorption bands of carbon dioxide are almost entirely masked by water vapor. And so that means that in the lower troposphere, CO2 isn't really very important. But it turns out that CO2 is important, and that's because the radiative balance that Fourier talked about isn't achieved at the surface. It's achieved high in the atmosphere, near the top of the troposphere, or the top of the atmosphere, as it's loosely called, top of the mass of the atmosphere. And the reason for this is that only at the top of the atmosphere can the CO2 really, can the long wavelength radiation escape to space. Because most of the infrared that comes off the surface gets scattered, gets absorbed, re-emitted, blah, blah, blah. It dances around, but can't get out to space except from the top. And so Suki Manabe and junior associate Gerald Wetherold, in a series of papers I've tried many times to try to read, but I do hope I remember the explanation, because when I visited Harvard, for them to have their fifth and last look at me before they decided to make me an offer, they took me out to dinner, and Mike McElroy, who was then the head of the department, asked me the question, how does the greenhouse effect work? And there was a deathly silence around the table while I gave the answer I had learned and is still often taught, which, while not being wrong, is at least inadequate and incomplete. And that is that the atmosphere absorbs infrared radiation and re-emits in all directions, including down to the surface, and that's the greenhouse warming. And that is an effect, but although, as Ray has pointed out, it has a negligible effect in the tropics, because the troposphere is nearly water saturated, and so there's no chance of that re-emitted IR to get back to the surface. So the real thing that's going on, as I understand it, is that when you put more greenhouse gas in the atmosphere, that level at which the radiative balance between the incoming and the outgoing radiation is achieved has to rise up to a higher level to get away from those greenhouse gases that are absorbing, to be able to escape into space. And when you rise that surface to a higher level, that's a part of the atmosphere where it gets colder as you go up. And so you're now have that balance at a colder temperature. And that means you're out of balance. And that sigma t to the fourth, that little 4, which is so huge, which drives the system towards that radiative balance and keeps it there, that is going to restore the temperature where the radiative balance occurs to that higher temperatures that it wants to be in radiative equilibrium. And so the top of the atmosphere has to warm up at that slightly higher level. And because the troposphere is a moist adiabat, you cannot warm the top of the atmosphere without warming the surface. And that's global warming, and it's real physics. Okay. Now, I'm going to switch gears. This idea that you can tell where old glaciers and ice sheets used to exist is a way of looking at the history of climate change in a rather crude way, but in a way that allows us to compare different times over the grand scale of Earth history, over, say, the last 3 billion years, as depicted on the bottom, with the last 800 million years shown expanded here. And all I've done is to separate Earth history into 3 climatic categories. The most common one is a situation in which there are no large ice sheets anywhere. There are mountain glaciers, but there are no large ice sheets. And that has, in fact, been true over most of geologic time, and most notably during this 1.5 billion-year interval that I've called the Proterozoic glacial gap. Now, the second climate state is the one we're in, and have been in for most of the last 35 million years or so. And that is the glacial interglacial state, which means we have a few large ice sheets. We presently have 2, Greenland and Antarctica. They're both composite, but they're integrated. And at the LGM there were 4. And so we've been going back and forth between 2 and 4. So a few ice sheets. And then finally, this third state is the panglacial state. And the panglacial state means there are large ice sheets on virtually all the continents. And I use panglacial as distinct from snowball Earth because panglacial it doesn't specify the extent of marine ice cover, which is still uncertain. So what you see here is a well-known pattern in the Phanerozoic, and then 2 periods in the Cryogenian and then somewhere early in the Paleoproterozoic where there were these panglacial periods. In the case of the Cryogenian, there are 2 of them that they're distinct. I'm going to have more to say about these, but I hope at the end I'll be able to say something about this and also about this one here. Okay, so these are the deposits of the Cryogenian ones. This is the way I categorize them. If anyone feels that the one that they're familiar with is out of place here, please let me know. This is my best current interpretation of which set these belong to. And I draw your attention to this area here in northwestern Canada, about which we've heard a couple of talks, and we're going to hear a couple more. And on Friday, I think we're going to hear what I think will be a talk that this meeting may be remembered for. And the reason I say this is that up until now, the discussion concerning snowball Earth has tended to be in rather generic terms. For example, when the ocean, or if the ocean is ice covered, do you have enough of a hydrologic cycle to drive dynamic ice sheets, as are required by the geological evidence? And it's very clear that there's dynamic ice almost everywhere. Another one would be, is there somewhere where the ice is thin enough for phototrophs to survive and even flourish, okay, under the snowball Earth condition, as is required by the fossil record? How much CO2 do you need to deglaciate? Or is CO2 even the initiator of deglaciation? Or is it more related to changes in the albedo of the ablative zone of the ice? These generic questions. Now, as a result of a talk on Friday, we're going to hear a date. And I think it's a very important date, despite the fact that it's using a method which is far from the most tested or reliable method. It's going to be an osmium isochron age. I was a little skeptical of isochrons, but the osmium isochron data the last few years has been starting to make some sense. And in this case, this date is consistent with all the other geochronological data that bear on the rock being dated that I'm aware of, including a fair bit of uranium-lead zircon geochronology. So I'm inclined to believe this date, and it's a game changer because it says that the 2 Cryogenian glaciations, the Sturtian and the Marinoan, are grossly unequal in duration. And I think if this proves to be true, it will have the effect of stopping us from talking about snowball Earth, and we'll start to talk about the Sturtian and the Marinoan and the non-glacial intermission between them about the specifics of Earth history. And I think that'll be a good step in the right direction. Okay. So this area is important because for an 800-kilometer length of the Mackenzie Mountains in the Northwest Territories and the Ogilvie Mountains in Yukon, you have a Sturtian age, the older of 2 Cryogenian glacial sequences called the Rapitan group. It's well studied and quite famous. And along this in the central part of the Yukon, in the Mount Harper Rift Basin, these glacial deposits sit upon and are interfingered with a bimodal complex of mainly subaqueous volcanic rocks, basalts and rhyolites. And that allows the onset, or at least the earliest glacial deposits in this record, to be dated at around 717 MA. And this is consistent with a number, with constraints on the onset of the Sturdian glaciation from a number of other areas, which say that it can't be older than about 720, 725. Now, it turns out that the onset of this glaciation is essentially coincident with this large mafic igneous province, which includes vast swarms of diabase or dolerite dikes, big complexes of gabbro sills, and an erosional remnant of a thick pile of flood basalts that were erupted principally between 718 and 716, although there's a fair bit of scatter, particularly in the Badleyite ages. Now, abundant and robust paleomagnetic data from these mafic igneous rocks place the paleoequator essentially right through the central part of this mafic igneous complex, which is a minimum of 2,300 kilometers in diameter. So this thing was erupted straddling the equator and places the Rapitan group, which includes ice contact deposits from glaciers that were grounded at or below sea level at a paleolatitude of around 17 degrees in the Mackenzie Mountains. Now, this is an attempt at a reconstruction of the paleogeography at this time, and I want to point out a couple of things. This is the Sturdian paleogeography, 715. This is the Marinoan one, and Marinoan termination, 635. Now, the first thing to point out is, and Adam talked about this morning, this migration of the Rodinia supercontinent to the equator, to low latitudes, and then the beginning of its disintegration around this time. So we have a lot of continents at low latitudes with access to ocean water, and that means intensified silicate weather and carbon dioxide drawdown. Now, in addition to that, this Franklin Large Igneous Province is erupted right across the equator on the east-facing continental margin of Laurentia, in other words, directly into the trade winds. You couldn't place a flood basalt in a better place for intense silicate weathering. And given the coincidence, or the very near coincidence in timing, I think that there is a reasonable possibility that this is the trigger of the Sturdian glaciation. Now, the paleogeography is also important in trying to understand why the Cryogenian went from non-glacial to pan-glacial, and you never seem to have any glacial interglacial situation. It was all or nothing. And the point about this paleogeography is not only do you have a lot of low latitude continents, but there are virtually no continents in the high latitudes. And that means to get any land ice at all, you have to have such extensive sea ice that you're very, very close to the snowball Earth ice albedo instability, after which the ice migrates rapidly in probably a decade or so in current GCMs to completely cover the ocean. So this paleogeography, I think, contributes to either having no ice or all ice. Okay, so here's a summary of the existing geochronology from 750 to 660 based on uranium-lead zircon dates. So these are the ones that pin the onset of the Sturdian glaciation, whose extent I've depicted in this line here. And this is the zircon, the existing zircon age constraints on the termination, somewhere around 660, 665. Now, the new data is important because it comes from the same glacial sequence where the onset was dated. And so you can't say that you're dating the beginning of one glaciation and the end of a different glaciation, and the Sturdian glaciations are all diachronous, because here we're dating the beginning and the end of the same glacial sequence. And Alan Rooney has recently obtained and will present on Friday a osmium isochron age from the base of the Twitcha cap limestone on the Rapitan group in this section consisting of 3 massive diamictites separated by well-stratified glacial marine deposits. And here is his isochron. And you'll note that it's indistinguishable from rhenium osmium isochron age for the equivalent cap limestone in Central Australia, for a minimum constraint on the glacial termination from an ash bed, zircons from the Datangpo in South China, which overlies the Sturtian glaciation, and a maximum constraint on the glacial termination from zircons from an ash bed right near the top of the type Sturtian glaciation in South Australia in the Williurpa Formation. And all four of these ages are statistically indistinguishable. And so for the time being, at least, I'm going to entertain the idea that the Sturtian glaciation began around 717 and ended sometime in the 659, 665 range, meaning that it lasted somewhere between 50 and 60 million years. And that's a long time. And as far as I can tell, there's no evidence of any non-glacial strata within that interval, although that's not to say there's evidence that the ice was present at all times. I'm not sure exactly what I just said there, but I'm going to move on. It means that the Sturtian and the Marinoan are grossly unequal in duration. And maybe there's a number of geochemical differences in these glaciations that might be related to that. And it also means that this non-glacial period between them, represented by hundreds of meters of carbonate strata in Namibia and Mongolia, some other areas, represents a relatively short window of geologic time that we can confidently correlate all over the world. Brian Harlan would be thrilled with this result because that is exactly why he was interested in cryogeny and glaciations as a basis for correlation. He wasn't interested in them as a climate phenomenon. No geologists were. So how to explain the differences? Well, one possibility would be the Sturtian is a snowball and the Marinoan isn't. The Marinoan is a different climate state, like the Jormungand climate state proposed by Dorian Abbott and Eiko Feucht and Ray Per Humbert. And I guess maybe Daniel Cole was on that article. I don't remember exactly. Jormungand is a climate state in which there's a band of open water near the equator. And it's stabilized because the ablative zone of the ice, it's simply a model in which you distinguish between the albedo of accumulation zone ice, which has snow on it, it's very bright, from ablative zone ice, which doesn't have any snow and is much darker. And if you do that, as this ablation zone migrates into the subtropics, which are arid anyway because of the descending arm of the Hadley cells, this expands and intensifies and stabilizes the ice line at this position in the climate model, in fact, in a number of climate models. Wouldn't that be ironic if the type snowball turned out to be a Jormungand? It might help explain why nearly all the iron formations are in the Sturtian glaciation, especially if the iron formations formed as a result by analogy with this water mass under the Taylor Glacier in the dry valleys of Antarctica. This is an amazing water mass that discharges at Blood Falls. It's got major amounts of iron, 3.5 millimolar. I mean, that's half the amount of calcium in modern seawater. It's got 50 millimolar of sulfate. I would never have believed that they could coexist. Very acidic, very salty, no oxygen. And the reason they so existed because someone turned the lights out, because there's a glacier sitting on this water. There's no hydrothermal source of the iron. It's just being scavenged out of the bedrock, which is Ferrar basalt. It's got iron in it despite all that sulfate because there isn't enough primary production to fuel microbial sulfate reduction, so there's no sulfide. That would be a way of making iron formations that would be quite consistent with snowball ice, but wouldn't be probably consistent with Jormungand, and might help to explain why you have iron formations in the Sturtian, not the Marinoan. So do I believe this? You know, I might if I hadn't read the abstracts to the EUG meeting in Vienna this year. Now, I didn't go to the meeting, so I didn't actually hear the talk, but the abstract says that when you put sea ice dynamics into the models that make the Jormungand disappears.
But that's been changed with the ocean dynamics, so you get it back.
Oh, good! So otherwise, I was going to be stuck with initial regolith or no initial regolith, which is still a very good idea. Thanks, Nick Swanson, Adam Malou. Okay, so a couple of words. I don't know how much time I have left, but I want to say one little thing to make a dig at the climate people in the audience about the Proterozoic glacial gap. And then I have an idea about this. I mean, everybody has to be interested in the Great Oxidation Event. And it's obviously the most important event in Earth history after the moon-forming impact. Maybe even more important than that. So I want to say something about that. So the Paleoproterozoic glacial gap. Now, so as you probably know, there have been attempts to try to account for this with reduced greenhouse gases, methane or nitrous oxide or things like that. I can't really comment on that, but here's another possibility. So this is the rate of star formation. And this might, yeah, you see, I knew I'd get this reaction. So there's a very tenuous climatic link that has a little bit of empirical support, but not very much. And that is that more cosmic rays do something in the troposphere that increases cloud nucleation, and therefore you get a higher albedo. It makes for a colder temperature. And so there is this, you know, whether it has any climate significance or not, nevertheless, this is an interesting graph. So this is a pair of articles, incidentally, which are very good and interesting articles. So this is the rate of star formation, which is thought to be, you know, scaled more or less with a cosmic ray production rate in the Milky Way disk. In other words, the stuff that, you know, might do something to us. And there are two maxima in star formation rate called ABC, and there's a notable gap in star formation. So you date stars by their metallicity. Okay, spectroscopy is how we know anything about everything. And so with spectroscopy, as you can tell how much metal there is in a star, and that uses a means of dating the star. It is all explained in this article. Anyway, there's this gap. Now, there are 400 million year bins here, but there's this notable gap in presumed cosmic ray production. And so, presumably, during this period, you'd have clear skies, or clearer skies. That's basically the idea. Okay. So now, we think that we have a good way of determining when significant amounts of oxygen first arrive. Like significant means 1/100th the present level of oxygen, by the collapse and disappearance of this mass-independent sulfur isotope fractionation, which is observed in older sulfide and sulfate sediments, and which never reappears. And so this is believed to mark an important turning point, at least important to geologists, because it's one of the few ways where we can actually say something confidently, we think, about oxygen. Now, because the atmosphere is well mixed, you would expect that this must be a global event. Okay? But if you look at the stratigraphy and the way people correlate the stratigraphy these days, it's a mess. And the two purple lines here are the disappearance of this mass-independent isotope signal in the Huronian, in the Canadian Shield, and in two sections in South Africa, in the Eastern Transvaal and in the Griqualand West area. Now, the Huronian is expanded to fit the time constraints for it, but in real terms, tectonically, it's probably compressed downwards towards this 2450 age here. The minimum age is 2220. And so it would appear that the disappearance of the myth signal, which is associated with the middle of the three glacial sequences in the Huronian, a single sequence, and therefore represents the minimum number of Paleoproterozoic glacial events. It's associated with the middle one, and its age should be somewhere in the 2400, 2420 range, I would guess. Whereas if you go to the Eastern Transvaal, this change, which takes place not associated with the glaciation at all, but with a major sequence boundary, a disconformity, very close to this osmium isochron age of 2320 in the middle Deutschland formation. Above the older of the two glaciations in the Eastern Transvaal and below the younger one, the Rietfontein, which is right underneath this terrestrial flood basalt, the Heckport basalts, which have detrital zircons as young as 2220. And in fact, there's lots of 2300 zircons in this sequence. Now, in the Griqualand West area, and it's difficult to correlate between these two things, there's another volcanic pile, a bunch of pillar basalts and hyaloclastite breccias, which have a lead isochron age of alteration that happens to be very close to that detrital zircon age from the Heckport. and for reasons that I don't understand, have been criticized only by the Rhodes University group, the late John Moore and his associate Harry Tsikos. Everybody accepts this correlation, and therefore they say that the Macchianini glaciation, which is associated with these volcanoes which give low inclination paleopole, in other words, low paleomagnetic latitude. So this is Joe Kirschvink and Bob Kopp's Paleoproterozoic snowball glaciation, the Macchianini. They correlate it with this one. So this means that the snowball event had nothing to do with the initial rise of oxygen in the atmosphere. And also, this age looks closer to 2300 and this 2400, and that doesn't sit very well. And also, you need at least 4 glaciations. So I think there's a lot simpler way of looking at it. If you take the MIF data from the Huronian and associate the change in the oxidation, the rise of oxygen, with the middle glaciation, the Bruce, the only one that has a cap carbonate, and if you, for no reason other than simplicity, say, well, let's correlate that with the snowball event in Hrickland West, which we know was oxidative afterwards because of the manganese formation. And then similarly, if we want to keep or mass-independent fractionation below and none above into the Transvaal, we would correlate the Macchianini snowball with not a glaciation, but with this disconformity. That's not a problem. Most of the Canadian Shield doesn't have any quaternary on it. Most of the Gulf glaciation in Namibia doesn't have any glacial deposits. They're all down the slope. The platform's almost bare. A little bit of lodgement till every once in a while. You don't recognize these beautiful fabrics in it. Okay? So I would associate with that. And then the meteorite bore also has the change in the MIF signal across that one. So we've got a situation now where there's only 3 glaciations, the minimum permissible number. The snowball event is the only glaciation in North America that has the cap carbonate and is directly associated with the first rise of oxygen. The two are hand in hand. I think that's a much simpler and potentially more sensible way of looking at this Earth history. And the only thing you have to do is relax that very poorly substantiated assumption that the Heckport and the Ongeluk are correlative. This is my last slide. You'll probably recognize neglect and hysteria. We should be heading towards rejection, which is when the Scottish glacial revival did all that systematic work that led to the acceptance even before the glacial isostasy was discovered by Jamison, just because the evidence was so overwhelming. This is a contribution from the modeling papers. As I said at the beginning, I think it's important to recognize that this whole increase in interest, these are papers just on the glaciation problem. It's not the only game in town on the Neoproterozoic for sure, but there has been a big increase that's associated with that. What's responsible for that? Climate models. In the first instance, the ice albedo instability problem that arose from some of the very first simple energy balance climate models by Budico and Sellers and others. And then the idea that a ice albedo instability is self-reversing and therefore geologically permissible. That's the James Walker, Paul Hayes, Jim Casting paper of 1981. And then Joe Kirschvink's first application of these ideas to the geological record. So this great interest about snowball Earth, this is climate scientists' contribution to geology, which is a nice counterweight to geology's contribution to the early development of climate science. Now, I still see an imbalance here. I mean, I'm really grateful to Gilles Ramstein and others for this hump, through the work of Yannick Donadieu and Yves Godéry, whose work on snowball initiation, fire and ice, looks much better than they could have ever imagined. And also Ray-Pierre Humbert and Jochen Marotsky here in Europe, and their team of young people, Eiko Voigt and Daniel Cole, Dorian Abbott at Chicago. But there's still imbalance. There's not nearly enough modeling. There are huge areas of this problem that are completely unmapped by models. Deglaciation, ocean circulation under snowball ice cover. There's some work just starting on that. surprising results. Not surprising once you see them, but it's not what you thought. And this is why we need models, not because models give us the right answer, but because they ask the right questions. And geologists aren't so good at that. Okay, so I would like to see more modeling. I think we need a better balance of that. We're badly in need of the modeling perspective on many of these problems. And unfortunately, 5 or 6 years ago, I know there were a number of young climate modelers that basically tried this area of science and got out of it because the Neoproterozoic geology community was so fractious. And I sense already today a much more positive attitude at this meeting here. Everybody's rowing the same boat. For all our differences, we're in the same boat and we're rowing together. And so I hope you enjoy this meeting as much as I'm sure I will. And thank you very much for your attention.
Well, Paul's still standing. He's not exhausted. And he's waiting for your questions, yes.
Right, oh, what can I say? What an absolutely amazing talk. Oh, sorry. Right,
The
what an
microphone
amazing
arrived
talk.
just in the right moment.
My question is this. Actually, it's a question for yourself. It's also a grumble to the organisers, who I have to say, up to now, have organised an absolutely brilliant symposium. The problem is that we've had a very, very long day in which we've been bombarded with a lot of quite amazing data. Then we had nothing, and then we had a wine reception, and now we had your talk.
And now we're hungry.
And to be honest, after your talk, I'm left a bit, flabbergasted. So my question is the essence of your talk on the internet anywhere, be it as a general review paper, a blog, a posting, or whatever? That's the slides. Come on.
I work hard on those slides.
Slides, a bit of notes. Is there any? Can you?
I believe it was recorded this evening, and I believe it's going on the GeoSoc website. Is that correct, Naomi? No. In fact, I was told not to dance around up here, and I've tried my best, but.
We can look at it on the GeoSoc website.
You can, yes.
Thank you very much.
Right.
Good talk.
I love your description of the stages of denial and acceptance. It's like Kubler-Ross and so forth. But I'm asking myself, where we are in this process for global warming, and whether that really fits in. You left out Arrhenius from your map of the
There are many
of
were
the
left
stages and understanding. But in fact, Arrhenius did actually understand the importance of the top of atmosphere budget. But it was a curious situation, which doesn't map quite onto your other examples. Curious situation is Arrhenius basically got the conceptual framework right, and he realized that you needed the top of atmosphere. But in the subsequent 60 years or so, up until Manabi, or more than 60 years, people have forgotten what Arrhenius already knew. And so that was the stage where, at the time of Arrhenius, there was a certain level of acceptance, just a little flicker of
but
denial.
that's neglect. I mean, Leslie got many things right about the geology, but nobody paid any attention.
Yeah, and
Esmark was, much better, and same story. Vaness too.
But after Arrhenius, there was a good 60 or 70 years of just where the subject was ignored,
Right.
And the few people who were thinking about it mostly got the basic physics wrong again. And then when Manabi came along and Plass came along, people started to pick it up again. But
so I say that before Manabi and before that sunk in, it was neglect, and then now it's acceptance, at least from the science standpoint. The public may not, but in science, I think it's accepted.
Yeah. And I just want to if anyone wants copies of all the critical papers leading to this understanding of global warming. Dave Archer and I do have a collection called the Warming Papers, which includes a translation, accessible translation of Fourier's paper, plus all the others.
Incidentally, the Fourier paper was translated into English and published in the American Journal of Science in 1833 or 34.
Thanks very much, Paul. It's a very impressive talk. But for me, sometimes it's very difficult to understand a small border. And I have to say, to be honest, in Uruguay and Argentina, we never found diamictite below the carbonates. We have 2 levels of carbonate and there are no diamictites at all.
Yeah.
So what do you explain that?
Well, an ice sheet transports material from its interior regions and moves them out to its periphery. So if you happen to be doing geology in the interior of the ice sheet, you're not going to see much evidence of it, unless you're lucky enough to see a glacial pavement. So it's true also in Namibia, the Great Gout glaciation. In most places, you don't see anything except the capped dolomite, which is much more extensive than the glacial deposits, because it's associated with the kilometer scale sea level rise that accompanies the melting of all that ice. You have to have at least 2 kilometers of ice on all the continents to explain that the ice was dynamic. And because the continental area is half the area of the oceans, that means there was a sea level fall of 1 kilometer and a rise by 1 kilometer after the glaciation was over, creating the greatest lake in the world, the greatest glacial Lake Harland, I call it, a kilometer meltwater lid on the ocean. That ocean was the residual snowball brine, minus 4.5 degrees, twice normal salinity. It's the most stably stratified ocean that ever existed. May have taken 10,000 years to mix that ocean. And a lot of geology was deposited in such a short time. Anyway, that's... yes, I think it's altogether to be expected that many areas under the thickest and most central ice will not have any deposits. You may be finding lucky locally a little bit of lodgement till, 1 meter or 2 meters in thickness. It looks like, I looked at it for some years and thought, oh, that's a well-developed sequence boundary. Well, I was right, at least as far as I went. But then when you measure the clast orientations, you see these very strong fabrics. And that's one of many other ways. There's a beautiful poster today showing fabrics from the older of the 2 glaciations in Namibia. So there are ways that a trained sedimentologist can recognize that, but ice everywhere doesn't mean ice deposits everywhere. Yeah,
Tony.
Tony.
Boring question for you, Paul, geology, and that's for the duration of the 717 to 663 age. That's assuming there's no amount of time at the base of the Rapitan that could be missing in terms of an unconformity.
Yeah, I mean, it's based on what I would think is probably the unusual situation where you actually captured the initial stages of that glaciation in the basal deposits of the Rapitan in that volcanically active area. There's no guarantee that the base of the Rapitan is going to be that age anywhere else, but in that area, and I believe that, and the reason for that is that there are other constraints on the age of the Sturdian in other areas that show it's unlikely, say in Oman or I can't remember them all, but it's South China, that it's unlikely to be older than 720.
And that is then
does rely on a correlation, but because the Rapitan is low latitude, I expect that if you've got grounded ice at sea level at 17 degrees, it's very hard from a climate perspective not to have temperatures below freezing virtually everywhere. It takes a while for the ice to build up everywhere, but it's going to. Yeah. So that's why I think it's so important that these ages come from the same succession. And there's nothing in that succession that doesn't look glacial or glacial marine.
No, I'm just concerned about the base.
Yep.
Over to Adam.
And we haven't seen the date yet. I hope. Where is Alan? He's not here. I have not met him, but I've heard very good things about him. Yeah.
He was just identifying himself. I have a question. That's Alan over there that just raised his hand.
Oh, is it that? It's that? Oh, okay. Good, thank you. Well done. Yeah.
Okay, so you talked about the Franklin large igneous province.
Yeah.
I wonder how you feel about its relative importance. You know, I can't help looking at that very long history of dike swarms, many of which were erupted at the equator, and didn't seem to do much.
I think that was the near-term trigger for the Sturdian glaciation. And you know, with the non-glacial period being so short, there was a recent article that says it takes 10 million years, not 1 million years, to draw down CO2 again. Then the Marinoan becomes, you could look at it as just a lapse back into the ambient Sturdian condition. And you don't need a trigger, although it does have this pre-glacial isotope anomaly that looks very much like the Isla.
But presumably it's a trigger on top of many other.
Yeah, on top of many, so the situation has to be primed. It's like the snowball, you know, we didn't have a snowball Earth at the KT boundary, but models suggest that if we were hit by a 10-kilometer bolide today, we'd be in a snowball Earth. Because the ocean today has a mean temperature of 1.5 degrees, and in the late Cretaceous was more like 10 degrees. And so the key thing is, can you keep a skin of ice from freezing over the ocean in the 10 years you have when there's a lot of dust in the atmosphere and there's not much sunlight? And so if the ocean is pretty cold to begin with, as it is now, models suggest you might be able to incite a snowball Earth that way. I don't think that's what happened in the Cryogenian, but it shows, it's just an example of how the prehistory is so important. That's why that's geology's greatest contribution to science. The idea that there are some things like our present Earth that can only be understood from the vantage point of its own history. You can know all the fixed laws of creation that you want. You will never be able to forward model and come up with this Earth if you don't know how it got there. Geology's greatest contribution to geological thought, or to intellectual thought.
Right, I think we're going to let Paul off the hook now and thank him very much indeed for his great performance.
Thank you.